Hello, this is Sachin Maheshri from Godavari College of Engineering, Jalgaon. Topic of presentation is electrical traction system. What is electrical traction system and its advantages? It has smooth starting without shocks. Then full driving torque is available from standstill. Third advantages of this electrical traction system is engine can be run at its most suitable speed range. This gives higher efficiency range. Then fourth advantage is characteristics of traction motor and generator are so chosen that the speed of the traction unit automatically adjusts according to the load and gradient so as to maintain the constant output and not to overload the diesel engine. And fifth advantage of this electrical traction system is electrical transmission does not only work as a torque converter but also work as a reversion gear. Now, what is electrical traction systems? The system which use electrical power for traction system, that is for railways, trams, trolleys, etc., is called electrical traction system. The track electrification refers to the type of sources supply system that is used while powering the electric locomotive system. It can be AC or DC or a composite supply. Selecting the types of electrification depends on several factors like availability of supply, type of an application area, or the service like urban, suburban, and mainline services, etc. The three main types of electrical traction system that exist are as follows. First is a direct current, that is DC electrification system, then alternating current AC electrification system, and composite type of system. Depending on this system, there are three types: direct current system, alternating current system, and composite system. In direct current system, the voltage range is shown, and alternating current system AC, this voltage range is shown, and composite system, there are voltage ranges as shown in this figure. Now, first is a DC electrification system. In this DC electrification system, as shown in figure, the current is collected from overhead wire through the pantograph and then given to the motor control unit. Through this motor control unit, DC motor is connected near to the wheel of that traction locomotive, and then through this motor control unit, this current is fed to the electric traction motor. The choice of selecting DC electrification system encompasses many advantages such as space and weight consideration, rapid acceleration and braking of electrical motors, less cost compared to the AC motors, less energy consumption, and so on. In this type of system, a three-phase power received from the power grid is decalculated to a low voltage and converted into DC by the rectifiers and power electronic converters. So the advantages of this DC type of system: in case of heavy trains that requires frequent and rapid acceleration, DC traction motors are better choice as compared to AC motors. Then second advantage of this type of system is DC train consumes less energy compared to the AC unit for operating same service condition. And third advantage of this type of system is the equipment in a DC traction system is less costly, lighter, and more efficient than AC traction system. Fourth advantage of this type of system, it causes no electrical interference with nearby communication lines. So the disadvantages of this system: first disadvantage is expensive substations are required at a frequent intervals because the rectifier unit is required for power conversion purpose. Then second disadvantage is the overhead wire and third rail must be relatively large and heavy. And third disadvantage is voltage goes on decreasing with increase in length. So second type of system is AC electrification system. An AC traction system has become very popular nowadays. It is more often used in most of the traction system due to several advantages such as quick availability of generation of AC power that can be easily step up or step down, easily controlling AC motors, less number of substation required, and presence of light overhead catenaries that transfer low current at a high voltages, and so on. The supply system of AC electrification includes single, three-phase, and a composite type of system. The single-phase system consists of 11 to 15 kV supply at a frequency of 16.7 Hz and 25 Hz to facilitate variable speed to the AC commutation motors. It uses step down transformer and frequency converter to convert from high voltage and fixed industrial frequency. The single phase 25 kV at 50 Hz is most commonly used configuration for AC electrification. It is used for heavy haul system and mainline services. It does not require frequency conversion. This is one of the widely used type of composite system wherein the power supply is converted to the DC to drive DC traction motor. As shown in figure, the AC electrification system shows where the current is collected from overhead wire and through this pantograph, and through pantograph it is given to the transformer where the voltage is stepped down up to the required level from by the transformer, and then it is given to the rectifier where rectifier rectifies the output comes from the transformer, and that output is in the form of DC. It is given to the motor control unit, and then through this motor control unit it is given to the electric traction motor, and then traction motor will run. Three-phase system uses the three-phase induction motor to drive the locomotive, and it is rated at 3.3 kV at a frequency of 16.7 Hz. The high voltage distribution system at 50 Hz supply is converted to this electric motor rating by transformer and frequency converter. This type of system employs two overhead lines, and the third track rail forms another phase, but this raises many problems at crossing and GG junctions. So advantages of this AC type of system is fewer substation is required, lighter overhead current supply wire can be used, reduced weight of supporting structure, then reduced capital cost of electrification. There are several disadvantages also. Significant of cost of electrification, then increased maintenance cost of line overhead wire further limits the clearance in tunnels. Upgrading needs of additional cost, especially in case there is bridges and tunnels. Then last disadvantages is railway traction needs immune power with no cuts. Similar to AC and DC electrification system, there are third system. There is third system. It is composite system. Composite system trains are used to provide the continuous journey along with the routes that electrified using more than one system. One way to accomplish this is by changing the locomotive at a switching station. These stations have overhead wires that can be switched from one voltage to another. Another way is to multi-system locomotive that can operate under several different voltage and current types. In Europe, it is commonly used for 4-system locomotive: 1.5 kV DC, 3 kV DC, 15 kV at a frequency of 50 Hz, then 25 kV AC 50 Hz is used. Then system of track electrification. There are 4 system of track electrification, that is direct current system, single phase AC system, 3-phase AC system, and composite type of system. First is direct current system, where the direct current 600 750 volt is universally employed for tramways in urban areas, and for mainline services the voltage range is 1500 to 3000 volt DC is used for mainline services. Both of these contact system are fed from the substation, which is spaced 3 to 5 km. For heavy suburban traffic, it is nearly situated in the distance 40 to 50 km for mainline services. Higher voltages of 1500 volt to 3000 volt, this system or substations themselves receive power from 110 to 132 kV 3-phase network. At this substation, this high voltage 3-phase supply is converted into low voltage single phase supply with the help of spot connection or V connection by 3-phase transformer. Next, this low AC voltage is converted into required DC voltage by using suitable rectifiers or converters. There are different converters systems is used. It may be noted that heavy suburban services low voltage DC system is abundantly superior to the single phase AC system due to the following reasons. The DC motor are better suited for frequent and rapid acceleration of heavy trains than AC motors. Then a DC train equipment is lighter, less costly and more efficient than the similar AC equipment. When operating under similar service condition, DC train consumes less energy than single phase AC trains. Then the conductor rail for the DC distribution system is less costly, both initial and maintenance, than the high voltage overhead AC distribution system. The DC system causes no electrical interference with overhead communication lines. Then single phase AC system. In this type of system, AC voltage from 11 to 15 kV at an frequency of 50 Hz or 25 Hz are used. If the supply is from generating station exclusively meant from the traction system, there is no difficulty in getting the electrical supply of 50 Hz or 25 Hz. If however electrical supply is taken from the high voltage transmission line at a frequency of 50 Hz, then the addition of step down transformer, the substation is provided with the frequency converter. The frequency converter equipment consists of three-phase synchronous motor which drives a single-phase alternator having 25 Hz frequency. The 15 kV, 50 or 25 Hz supply is fed to the electrical locomotive via a single overhead wire. A step-down transformer carried by the locomotive reduces the 15 kV voltage to 300 to 400 volt for feeding the AC series motor. Speed regulation of AC series motor is achieved by applying the variable voltage from the tapped secondary of the above transformer. Low frequency AC supply is used because apart from the improving the commutation properties of AC motors, it is increased their efficiency and power factor. Moreover, at low frequency line reactance is less, so that the line impedance drop and hence line voltage drop is reduced. Because this reduced line drop, it is feasible to space the substation 50 to 80 km apart. Another advantage of employing low frequency is that it reduces the telephonic interference. Then the third type of system is three-phase AC system, where it uses the three-phase induction motor which works on 3.3 kV at a frequency of 60 Hz supply. Then substation receive power at a very high voltage from three-phase transmission line at an usual industrial frequency of 50 Hz. This high voltage is stepped down up to 3.3 kV by transformer, whereas frequency is reduced from 50 Hz by frequency converter installed in the substation. Obviously, this system employs two overhead contact wires, the track rail forming a third phase. Induction motor used in this system are quite simple and robust and give the trouble-free operation. They possesses the merit of high frequency and operating as a generator when driven at a speed above the synchronous speed. Hence, they have the property of automatic regenerative braking during the descent on gradient. However, it may be noted that despite all its advantages, this system has found much favor, and may be noted that despite all the advantages, this type of system has not found much favor and has in fact because of its certain inherent limitations. There are certain limitations in this system. The overhead contact wire should become complicated at crossing and junction is the limitations of this system. Then second limitation is constant speed characteristics of induction motor are not suitable for traction work. Third limitation of this type of system is induction motor have speed torque characteristics similar to the DC shunt motor, not in DC series motor. Hence, they are not suitable for parallel operation, because even with the little difference in rotational speed caused by unequal diameters of the wheel, motor will become load very unequally. Then fourth type of system is composite system. It is again divided into two types: single phase to three phase system are also called as condo system, and single phase to DC system. First system is condo system. In this type of system, single phase 60 kV, 16 kV, 50 Hz supply from the substation is picked by the locomotive through the single overhead contact wire. Then it is converted into three phase AC supply at the same frequency by means of phase converter equipment carried on the locomotive. This three-phase supply is then fed to the three-phase induction motor. As in the complicated overhead two contact wire arrangement of ordinary three-phase system is replaced by a single-phase wire. By using the silicon control rectifiers as inverter, it is possible to get the variable frequency of three-phase supply at half to 9 Hz frequency. At this low frequency, three-phase motor develop high starting torque without taking excessive current. In view of this above, condo system is likely to be developed further. Then second type of system is single phase AC to DC system. In this type of system, the combines advantages of high voltage AC distribution and industrial frequency with the DC series motor traction. It employed overhead 25 kV 50 Hz supply, which is stepped down by the transformer installed in the locomotive itself. The low voltage AC supply is then converted into DC supply by rectifier, which is also carried on the locomotive. This DC system is finally fed to the DC series traction motor fitted between the wheels. The system of traction employed 25 kV 50 Hz single phase AC supply has been adopted for the all future work track electrification in India. Nowadays this type of system is used in India, 25 kV AC system. Then next is a speed time curve. Depending on the different services, that is urban, suburban and mainline services, this speed time curve draw where time on x-axis and speed on y-axis. We will draw the speed time curve. There are several parts like rheostatic acceleration, then acceleration on speed curve, then free running, then coasting and then braking. We'll see one by one. First is constant acceleration period. It is from 0 to T1. It also called the notching up period or starting period, because during this period starting resistance of motor is gradually cut out so that the motor current is maintained nearly constant, which produces the constant acceleration, alternatively called rheostatic acceleration or acceleration while notching. Then second curve starts, that is A to B, at a time T1 to T2. This acceleration commences after the starting resistance has been all cut out at the point T1 and full supply voltage has been applied to the motor. During this period, the motor current and torque decreases as train speed increases, hence acceleration gradually decreases till torque developed by the motor exactly balanced that due to the resistance of the train motion. The shape of the portion A to B, the speed time curve depends primarily on torque speed characteristics of the traction motor. Then third one is free running period, where the time is T2 to T3 and curve BC starts. The train continue to run at its speed reached at point T2. It represented by a portion BC in and is a constant speed period which occurs at level track. Then fourth point is coasting period, where time is T3 to T4 as shown in figure. That is curve starts from C to D. In this coasting period, power of the motor is cut off at the point T3 so that the train runs under its momentum, the speed gradually falling down due to the friction, windage, etc. During this period, the retardation remains practically constant. Coasting is desirable because it utilizes some of the kinetic energy of the train which would otherwise be wasted during the braking. Hence, it helps to reduce the energy consumption in the train. And then a last curve starts, that is braking, T4 to T5, that is D to E point. Then at the point of T4, brakes is applied and then train is brought to rest at the point T5. It may be noted that the coasting and braking are governed by the train resistance and allowable retardation respectively. This is nothing but the speed time curve of the system. Then some definition comes depending on the speed time curve. First is cruise speed. What is cruise speed? It is denoted by Vm. The maximum speed attained by the vehicle during the run is nothing but the cruise speed. Second definition is average speed. What is average speed? the mean of the speed from start to stop, that is the distance between two stop divided by the actual time of run, is known as average speed. Average speed is nothing but the distance between two stop in kilometer divided by actual time of running in hours. Then third definition is schedule speed, the ratio of distance covered between two stops and the total time of run including the time of stop is known as schedule speed. It is denoted by VSH. It is nothing but the VSH equal to distance between two stops in kilometer divided by actual time of run in hours plus stop time in hours. So the schedule speed is always smaller than the average speed. The difference is large in case of urban and suburban services, and it is negligibly small in case of mainline services. This is all about the part 1 of electrical traction system. Thank you.